All right, it's 12:55. It is time for our keynote for today. Our keynote speaker today is Don Eyles, software engineer and artist, author of Sunburst and Luminary, an Apollo memoir. His talk is entitled Flight Software Comes from Mars. Don Eyles built flight software for 32 years at the MIT Instrumentation Lab and in the Charles Stark Draper Laboratory in Cambridge. During the Apollo project, he wrote onboard software for the guidance computer on the Lunar Module, including the code that guided the spacecraft during the descent from orbit to the lunar surface. He originated a sequencing system called Time Linear, also called UIL, that is currently in operation on the International Space Station. He retired in 1998 and is active as an artist in Boston. His memoir of the Apollo project, titled Sunburst and Luminary, was published in 2018. And it is my pleasure to offer Don Eyles. It's all you, Don.
Well, thank you. It's a pleasure to be with you today. I'm a voice from the past, I suppose. I am humbled after listening to part of the previous presentation to realize that my vocabulary may not be current in terms of flight software, but I hope it will work in the other direction, where the possibly dated way we thought of things will still get through. Let's go to the next slide. There are various places to start the story, and I like doing it right here, almost 100 years ago. This is Doc Draper on his way from California to Cambridge, obviously living off the land on the way. Next slide. He got to Cambridge. He was going to investigate Harvard, but instead he stopped at MIT and never left, compiling the longest transcript anyone ever had. And getting interested in instrumentation and forming a group around him who worked on that. One of his first big contribution to the national interest, if you will, was the Mark 14 gun sight, which made it much easier for anti-aircraft gunners on ships to shoot down the planes that they were being attacked by. And that's what you're seeing in that right-hand picture. In the distance is the battleship South Dakota, equipped with Mark 14 gun sights. Next slide. He moved on. He and his group moved on to considering the problems of inertial guidance per se. And this is in 1953 when the SPIRE, that stands for Space Inertial Reference Equipment, is being installed in MIT's B-29 bomber. For a flight across the country, which proved that it could be done, that navigating that way could be done. They arrived in LA with a position error of about 8 miles. They were there, his group was there for a conference on self-contained guidance systems. And after listening to various speakers explain the difficulties, Doc Draper impromptu stood up and said, well, we just did it. Next page. Okay, this was a shock, of course, to everyone, including my colleagues to be at MIT, Sputnik. And go to the next page. And this was the response. And I'm using a different color red. That's MIT maroon, if you will. This is the reaction at the lab, which took place within a few months. This slide is dated January 1958. Was to conceptualize a Mars reconnaissance vehicle that would leave Earth, go to Mars, come back with exposed film, which it would then re-enter with. Next slide. And the paper that figure comes from is the one that's in the middle of this page, and that contains the statement, a highly versatile and reliable digital computer, light in weight and with an extremely low average power consumption, appears to be a fundamental requirement for the system. Reasonable extrapolations of current researches in core memories and logic should produce such a computer by the time it is required, which I think was a fairly daring statement in 1958. Next. The two people that were most concerned with the papers on the previous page are these two, Hal Lanning and Dick Batten, who were very much on the scene by the time I joined. Hal created the first compiler in history in about 1952. We've already spoken about the interplanetary probe that he was instrumental in conceptualizing. And he also, as we'll hear about a little later, created the operating system for the Apollo guidance computer. Dick Batten was more the equations man, the legacy, with the legacy of Kepler and Newton. Among his accomplishments, one of them was to create the first gravity assist trajectory, which he did about 1961. He also taught astronautics to a number of astronauts in his MIT class, and he was the overall chief of Apollo software. Next. When he told his wife, she said, "Please don't tell anyone." This is the computer that resulted from the paper I cited earlier. There was a continuous process. The lab managed to get some money, I think, from the Air Force and started designing computers. At the time the Apollo project started in 1961, there was a breadboarded computer with 4,000 words of memory, fixed memory, and 128 words of RAM, of read-write memory. Indeed, this computer was reliable. This is the AGC, 1 cubic foot in its biggest version, 36K words of memory. Those are 15-bit words plus a sign bit. So 1 word equals 2 bytes in effect. And it never had any failures. And I don't think that's an exaggeration. Next slide. Two of the things that helped it become reliable, not to speak of its other constraints, were the use of integrated circuits, which was extremely daring when it was decided on, because those were not at that time famed for reliability. But a lot of work was done that improved with the manufacturers to improve the reliability and create enough of them for the computer and also for the peripheral ground test equipment. Were all used the same type of IC, which was a double triple input NOR gate. Another factor in the reliability is that the fixed memory, where the program was stored, was done in the form of wire rope. The sense lines carry information to the logic, of course. A line that runs within the core is a 1, outside of the core is a 0, and the cores were selected by those inhibit lines at the bottom, turning each core into, in effect, a transformer. I won't try to explain that further now, but it resulted in a memory that resembled a rope made of copper wire. Next slide, please. Another thing about the picture of the computer a couple of slides ago was that it included a human interface, which is one of the factors that was left out of the Mars study. This is the general purpose way of communicating with the computer. And this applied both in the cockpit of the lunar module, but also when we were testing it on Earth. In our hybrid simulator, which I'll tell a little bit about later. There are 3 5-digit general purpose registers, and the astronauts had to know, according to the noun number, which is 63 in this example, had to know what each of those meant. The bottom number is altitude in feet. The middle number is altitude rate in feet per second, 92.7 right now. And the top number is speed. In other words, the absolute value of the velocity vector. Next slide. And the lights, I should have said, to the left for various special functions. Here is comic relief. This is how the crew interface was visualized at the very beginning of Apollo. You can see the two extremes there. And a little later, I'll show you a slide that shows you what the crew looked like during the busiest period of a lunar landing. Next slide. Excuse me. So we arrive at, let's say, the year 1966 or thereabouts. Along with the computer development was the development of the inertial measurement unit. On the left, in I believe 1955, you see Dr. Draper explaining the one in the B-29 to Eric Severide, the journalist. On the right is the Apollo version, quite a bit smaller. That case is about 1 foot in diameter. In there, in that lumpy middle, are 3 accelerometers and 3 gyros. And you can see the gimbals that hold that core called the inertial platform or the stable member that hold it in its geometrical orientation, no matter how the spacecraft maneuvers around it, thus providing the equivalent of a compass, and so on. Next. And there's the computer with its interfaces within the spacecraft and with the ground. Some of those arrows are one way, like an engine command. Some of them are 2 ways, like the communication with the DSKY, the display and keyboard that I showed you a little while ago, with the cockpit switches at the upper left with the IMU, the inertial measurement unit, which we just looked at, and with the alignment telescope that was used for aligning that IMU to a given orientation with respect to the stars, in other words, with respect to inertial space. As I say, there's a communication with ground control. However, the Apollo guidance system was baselined to be capable of doing its mission without communication from Earth. And arguably, it showed that it could do that. It was always the onboard solutions that were operated, executed, and those were double checked by ground information from the ground, but it was the computer's solution. Next slide. This is where I enter, July of 1966. That's baby-faced me. George Cherry, who hired me. George was a shy type when it came to photos, and that's the only one that the Draper Laboratory could come up with. And I was assigned by George to work with Alan Klump, who had the job of turning an equation that Cherry had originated into a working system for guiding the LEM during the landing phase, which is the descent from lunar orbit to the lunar surface. And that's the building we worked in. Next. One thing about working in those days was that if you're picturing any sort of terminal on our desks, any sort of PC or anything with a cathode ray tube or any other display, you've got it wrong. We didn't have those. What we stared at when we were thinking about the flight software was paper. And by the way, I'm all for paper. I think it's a wonderful invention that would awe us now if we had gotten to this point without it. So easy and cheap to put information on it. You can even take it in the bathtub with you. Maybe not this particular book, however. That's about 6 inches thick in that version, but it was all there. Our computer was small enough, with room for something like 30,000 lines of code, that it would all fit in one book. So the answer was in there if you could find it. You didn't have to go chasing a million documents, shall we say. On the right is a copy of Memo 9, a famous memo by Hugh Blair-Smith, which was essentially the language manual for one of the 2 languages. Next. For one of the 2 languages we used in the computer. This slide shows you that was the language called BASIC, which was the assembler language. You can see a portion of that page is in that language. We also had an interpretive language, essentially a family of subroutines and a way of writing it in sort of a list processing manner, where opcodes were listed and then the operands were listed. And we also, in the assembler, which was Hugh Blair-Smith's creation, there was also very good capability for putting in comments, and which were a great help if you were trying to understand code that was not your own or even was your own. Next page, please. This is a chart from the Hugh Blair-Smith memo, and I've put the citation down below if you want to look it up. It's, I think, probably somewhat fascinating. But at any rate, with a 15-bit word, they were able to eke out 30-something different opcodes using a number of subterfuges. One of them was the operations on the bottom half of this chart, which had to be preceded by an instruction called extend that essentially added a bit, and right there doubled the number of operation codes. Next slide. And the other ways of making it fit was the way the erasable and fixed memory were arranged, where there were certain parts of each of those memories which were always in place, shall we say, but another part which could be switched to any of several banks of memory. Now, that may sound burdensome, you know, if you needed to deal with something that was in a different bank, and there were subroutines to help you do that. On the other hand, by allocating the memory, both the fixed and the erasable memory, you could avoid that being a serious issue. And it allowed the all of memory, the entire 36K words, to be addressed with the appropriate instructions. Next slide, please. And I've already said we didn't have terminals. This is where we programmed the Apollo guidance computer. This is an IBM 026 key punch machine, and using one of those became second nature. I rather think that every computer science student in college should get to use one of these at least once in his life, just as an art student may have to employ some primitive technique as part of his or her training. But it became second nature to use this. I won't go into it to any great detail. Cards originating on the right, come down, pass from right to left. They pass through a reader after they are punched, so that if you make a mistake, you can bring in a new card, hold down the duplicate key until you got to the column that was wrong, and then proceed from there with what was correct. And then it became automatic to reach out with your left hand and grab the faulty card and chuck it in the wastebasket that was always there. Next. Testing. How did we test our software? Well, we had various ways of doing it. One that I couldn't think of a good slide for was our all digital simulation, which could be called the gold standard. It was, it embedded our programs for the AGC in an emulator, and that emulator was embedded, if you will, within a set of programs that played the role of the environment of the spacecraft and of the physics, shall we say, so that the software, the emulated onboard software, was receiving the inputs that corresponded to its outputs, so to speak. That could not keep up with real time, however. I recall that on IBM, on Honeywell 1800s, in the early days, it took something like 4 hours to run a complete landing of about 20 minutes. We also had this simulator, which, as you can see, allowed for a man in the loop and could keep up with real time because of the use of hybrid computers. That's a Beckman analog computer in the lower right image. You can see the plug boards that amounted to the program, and the strip chart recorder, the sort of polygraph with scrolling paper and needles that swiggle back and forth, that were the way you got information out of the analog computers. The upper right image, you can see that there is a diski, which I showed you before, mounted on the front of one of the cabinets. Hidden inside that cabinet is a real Apollo guidance computer. The rack on the right provides the equivalent of the fixed memory, so that a tape could be read into that, and you could then, using that diski, or using the cockpit, which was immediately upstairs, what you can see on the left, you could fly landings or any other phase of the mission. Next. Now, my specialty was the descent, working with Alan Klump. I did most of the coding. He did most of the analysis, although those roles did blur at times. This is to show you what the lunar landing looked like. It consisted of three main phases, beginning at the low point of the lunar orbit that the LEM was in, which came down to about 9 miles altitude, approximately. And at that point, at the appropriate point, as computed on board, the engine was lit. Initially, thrusting was directly against the direction of motion. But gradually, as the guidance equation controlled the attitude and the throttle, the LEM moved to a more straight up posture. But that happened in phases. The first phase was called the braking phase. Again, it started at that moment called PDI, which I think you've probably heard those initials in stage or screen, shall we say, at a velocity of about 5,600 feet per second, which is lunar orbital rate, and a distance of around 250 nautical miles from the intended site. During the braking phase, a couple of important things happened. One of them was that the landing radar had to lock onto the surface to measure velocity across the surface and altitude. The inertial guidance was great, but it was not good enough when you got in vicinity of the moon to trust it to the foot, shall we say. In fact, it was normal for the landing radar to have to put in a correction of something like several thousand feet. And similarly for the Doppler radar that measured the speed across the surface. So the radar had to lock on by a certain point, or the landing had to be called off. That actually came into play on Apollo 14 a little later. And the other thing that happened during the braking phase was throttle down. I think the next slide, please. We may want to go back to that previous one. What throttle down is, not yet, go to the next. Thank you. What throttle down is about is the fact that there was a constraint on the way the LEM's descent engine could be operated. There was a region between roughly 60% and maximum that was no-go, because it was thought that the nozzle would erode excessively in that thrust regime. So the thrust profile during a landing looked like this, where for a long period during the braking phase, we simply ran the engine at its maximum. And finally, when the guidance equation concluded that the thrust needed to be within the fine control, below the fine control threshold, if you will, something would happen called throttle down, where in one swoop, the engine would be throttled down from maximum to somewhere in the 50s. And from then on, if all went well, the engine would stay within the controllable zone. So go back to the previous, thank you. So throttle down would have to happen. Throttle down was a period of excitement during these lunar landings, because it was a pretty good indication that the guidance system was doing what it was supposed to do if throttle down came when it was expected within a few seconds. And it did. At any rate, excuse me, at any rate, a bit after throttle down, we got to high gate, as we called it. At that point, the guidance equation shifted to a different set of targets. And the immediate result of that was a pitch maneuver that brought the limb into an attitude where, for the first time, the astronauts on board could get a really good look at the lunar surface in front of them. And that pitch over was another one of those moments of extreme excitement, especially for the astronauts on board. It's the place where in the transcripts you find exclamation point after exclamation point, as they usually were able immediately to recognize the pattern of craters ahead and be able to orient themselves and to do what they could to bend the limb's trajectory to the exact spot they wanted. Because also during the visibility phase, we gave them the ability to do that, to look through a reticle on the left window. The commander on the left did this, to see where, in fact, the guidance thought it was taking the limb. And if they didn't like that spot, they could tweak the rotational hand controller that wasn't needed at that moment for anything else, to shift the landing site by a discrete amount, uprange, downrange, left or right. Neil Armstrong on Apollo 11 never used it. Pete Conrad on the next mission used it a lot. And finally, the visibility phase would end at the discretion of the commander at the point where he decided to take over semi-manual control. Usually that was in the region of around 400-foot altitude. At that point, he's oriented himself. He sees where he wants to go. He decides to use his stick and rudder skills instead of letting the automatic guidance take him down to all the way to the 100-foot altitude. He would then maneuver to be directly above the spot where he wanted to touch down and descend. I called it the semi-automatic phase. We called it P66. The semi-automatic phase, because the astronaut controlled horizontal movement across the surface using the hand controller, this time for attitude control, thus being able to vector the thrust left, right, or in any direction and scoot across the surface. Meanwhile, the computer regulated the throttle to maintain a constant descent rate. Next slide, please. Okay, we already talked about that. I promised you this before. This is the cockpit of the limb during the visibility phase. I mentioned that we showed the commander where he was going, where the limb was going, and this is how that worked. You see that there's a scale painted on the left window, and the disky, there's a blow up of the numeric data. The disky is providing an angle, in this case 43 degrees, computed by our software. And by looking along that scale after aligning his eye properly, then at the 43-degree mark should be the spot on the surface where the limb was going to end up. You could compare this, I suppose, to those cartoons I showed you earlier, and it's probably more like the second one with the astronauts fully occupied than the other way around. Next slide, please. Okay, I'm going to talk a little bit about what's actually going on in the computer and how that was coordinated, shall we say, how the operating system, although we didn't use that term, how that worked. This lists the descent functions, And the heavy lifting took place on a 2-second cycle. That consisted of navigation, reading the accelerometers, doing the average D computation, incorporating radar data, if by that point we had locked on, guidance, which was the guidance equation, allowing for the redesignation in the visibility phase, throttle control, which was not entirely simple, and the output of the new attitude command to the autopilot. And also within that 2-second cycle was the crew interface, the computation of any numbers that needed to be displayed, refreshing the DSKY, and refreshing or providing the data for refreshing the analog displays. I put analog in quotes. They just looked analog, sort of steampunk style gauges on the cockpit that were really operated by the computer as a backup for the vital information of altitude and altitude rate. And when they got quite low to the ground, as an indication of horizontal velocity across the surface. And of course, responding to crew inputs. In the background, as we thought of it, we who were concerned with guidance, were things that were going on in hardware interrupts. Among those were the digital autopilot, which stabilized the vehicle in whatever the commanded orientation was, and up-down telemetry, which transmitted every 50 milliseconds every 20 milliseconds, 2 words of memory to the ground, making a total list over a 2-second cycle, making a total list of, I believe, if I said it right, 200 different words that came to mission control from inside the computer. Next. So I earlier ascribed to Hal Lanning, among his many accomplishments, the thinking up of the AGC's operating system, which we call the executive. And that consisted of 2 types of software entity. Tasks, those were mandated to be very short in time, but they were sure to occur on time, within, 100th of a second or so. And then there were jobs, which could be of any size, and they had a priority. They were assigned a priority when they were scheduled, and it could be changed. And higher priority jobs could break in on lower priority jobs. We rejected a boxcar type of executive, which some people at various times have argued for, where what needs to be done by the computer is broken up explicitly into different segments, which are assigned slices of time. That absolutely would not have worked for us. There would have been too much wasted time, too much overhead for that ever to have worked with the AGC. And we didn't really believe in it. We thought this system where we had these jobs, yes, they were competing with each other. Yes, it was slightly less deterministic than some people would have liked, but it made sure that we wasted none of the CPU, because we really did need all of it. Now, laid on top of the executive was something called restart protection. We had to try to design the system in such a way that we could get past a power transient. And that led to the creation of something called restart protection. And it was later turned to as sort of a last resort if the software reached some sort of impasse. Jobs that were considered vital, you remember that, well, on the same page as my explanation of what jobs were. Jobs that were considered vital were restart protected, which meant that waypoints were recorded at strategic points. When I say strategic points, I mean points such that if execution returned to that point, the accuracy of the computation would not be affected, which sometimes forced us, of course, to save the new value, do a restart point, and then plug the new value into the old value, so to speak. Upon a restart, execution resumed at whatever the last recorded waypoint was. And this was all implemented independent of the executive, which I think might not have been the case if this had been more thoroughly thought through at the beginning, but it turned out to be a good thing on Apollo 11, as I will explain soon. Next slide. Okay, how did that work in actuality and in reality? And the way the usual pattern was, if to schedule a task, in this case you're seeing the redax task, which reads the accelerometers, to schedule a task at the regular intervals, and then within that task a job could be scheduled to do the computations that followed upon the accelerometer reading and the navigation and the new state vector and so on. So ignoring the things that were going on in interrupts or in other jobs, this was the pattern taking place during the lunar landing when things were working right. And you can see the order of the different functions within the service or job. And if all went well, the service or job, of course, would finish, and there would be a certain amount of slack before the next redax and the next service or job started. Now, remember this image, because a little later on, you'll see how it could malfunction in a certain case. Next. This is a list of the jobs that were going on during the descent. There's a little bit of a paradox here in that servicer, which, as I've just described it, was kind of the most important thing going on, had the lowest priority. That was because these other much shorter jobs needed to be able to break in on it. And so they had to be allowed to. So priority was not always a measure of importance. Another thing here is that that last job, Mondo, that was not restart protected. That was not considered vital. That was a job that was created whenever the astronaut wanted to use the diski to monitor some parameter that was not within the default display. You remember I showed you the default display during the braking phase of velocity, altitude, rate, and altitude. But if the astronaut, for example, wanted to see the difference between the altitude measured by the radar and the altitude of the inertial guidance, he could call up a different noun using verb 16, and to service that request would require a new job. So that's what that Mondo job is. Next slide. Now I'm going to talk about missions a little bit. LIM 1, well, it's kind of a forgotten mission. It was the first unmanned test of the Lunar Module. And as a software developer for a very visible flight project, it was the first time any software I had written had flown. It was called a success, the mission, based on the fact that the engine firings were executed properly, the engines held up. But it was also an embarrassing failure that was blamed on a piece of software that I happened to have written. This was a piece of software called the Delta V monitor that was a small thing tucked into a servicer, which looked at the thrust as it accumulated after the engine was lit. And the requirements document said that it was to check 3 times at 2-second intervals. And if thrust had not come up, an engine off command would be sent, I guess, to safe the engine. Unfortunately, an operational decision was made that we didn't hear about to delay the arming of the engine. As a result, it was slow to come up to thrust on that engine. And as a result, the Delta V monitor concluded that the engine had failed and sent the engine off command. And that was it for our software, because ground control, instead of trying to recycle with the software, decided to assume direct control from the ground and conducted the engine firings that way. But our software was in the doghouse. We were popularly blamed, even though we had followed the requirements. And when I say it stimulated a healthy skepticism on our part, that was part of it, not to necessarily believe without question everything the requirements said. Why, for example, was it so urgent to send that engine off command? And after this mission, a change was made to the software such that we would not send that command. That would have to be done by the crew with their engine off switch if it was going to be done. What this meant for Alan Klump and I was that there was going to be no dry run for our lunar landing code, because this mission did carry software that would have been a facsimile of the lunar landing. So LIM 1, also known as Apollo 5, was sort of an educational experience, shall we say. Next slide. That's the Apollo 11 crew. Next. And that's the disky displaying the famous 1202 alarm. That was the moment when the lunar landing seemed to almost go off the rails. Let's go to the next slide. This is a plot of the computer's duty cycle during the landing. And you'll see that we have a margin at the beginning. After throttle up and guidance, our margin is down to something on the order of 15%, maybe a little more. And much later in P64, it goes down to less than 10%. Next slide. Meanwhile, on Apollo 11, a flood of pulses was coming into the Lunar Module guidance computer. And why was that? It was because the checklist showed the rendezvous radar, which, if you're thinking, what did that have to do with the landing, then that's a good thought. But the radar was on, and the switch, according to the checklist, was in the slew position. At one point, it was switched to the auto position. What that meant was that the angle resolver at the lower left was being given a reference signal that was incompatible with our system, with the primary guidance system. And as a result, especially since, as it happened on that mission, those two reference signals were very much out of phase. It meant that enough pulses were coming to our computer to occupy about 13% of its duty cycle. That was because counting the pulses so that the software could see the position of the shaft and trunnion of the rendezvous radar antenna, that was done by stealing computer memory cycles, 11 microseconds each. And that was enough. That added up enough to make a serious dent in the CPU available to the software. Next slide. I ask you to remember how Servicer looked when things were operating as they should. This is how it would look during Apollo 11. Now, there were 5 alarms in Apollo 11. The first 2 were in P63 when we had a margin of something like 15%, 14%, which should have accommodated the load that the glitch was putting on us. But at one point, Buzz Aldrin did want to see the radar correcting the state vector. So he used noun 16 to select a different, verb 16 to select a different noun. I believe it was noun 68. That created that job we looked at earlier called Mondo. That pushed our margin below 13%. Therefore, we had an alarm. Now what happened when the alarm occurred? Now, I've maybe gotten ahead of myself, because the alarm occurred because the queues in the executive system became full, and it was not possible to schedule another job. So what happened during P63 was, and the cure for that, it was one of those software impasses I referred to. The cure for that was to create a software restart where the entire procedure of restarting the computer was going through, but because software asked for it. When that occurred, the queues of the executive were flushed, as you can see in those lower pictures. And we restarted processing at the last recorded waypoint. What was happening was that the displays were being cut off by the fact that there wasn't enough time and servicer was not finishing. Fortunately, we kept flying because the cutoff apparently always occurred after the throttle and attitude commands were issued. But there were funny things going on with the displays. During the visibility phase, it went away for about 10 seconds. During the briefing, Armstrong laughed about it, said he didn't think it was ever coming back. As I said, the first two alarms cured themselves, if you will, by the fact that since it wasn't restart protected, the Mondo job was shed. The alarms that occurred during P64, during the visibility phase, kept recurring at intervals, as indicated by the two plots below, because even without the addition of the Mondo job, we did not have enough margin to accommodate the malfunction. Next slide. I probably could have done a better job of explaining Apollo 11. It's maybe the prime teaching moment for the Apollo software. I've twice in writing described the problem. There's a paper online on my website, doneyles.com/LM. And there's also, of course, my book, and they both describe that from a different angle. But Apollo 11 accomplished, even though we landed 4 miles from where we intended to, things got to be more fun, shall we say. And the next goal, shall we say, was to make a pinpoint landing, to really land where we wanted to. And that was Pete Conrad's mission. And the goal was to land next to one of the unmanned surveyor spacecraft that had previously landed on the moon. One of the spacecraft that had settled the question of, was the moon made of dust that the spacecraft would sink into? And fortunately, no. And as you can maybe tell from this picture, this was a fun crew. We had crew training meetings with each of the crews. Well, not all of them, but with 11, 12, and most of the others. And the one with this crew was, believe me, was a barrel of fun, but also serious enough. The software implications of trying to make a pinpoint landing were the fact that there was no good way. The radar could measure the speed across the surface and correct that, and could measure altitude and correct that. But there was nothing on board except the human eye that could recognize a place and try to go land there. And for the human eye to pick it up, you had to know pretty much, you had to be pretty much in the right spot at pitch over at the beginning of the visibility phase for them to be able to recognize where they were. And as I said, Apollo 11 was about 4 miles off. How did we fix that? Well, it turned out that ground tracking, when the LEM came around the side of the moon for the last time before making the landing, that was a good setup for ground tracking to pin down the velocity of the LEM and its exact position. And this was the one case where help from the ground was necessary. We could not make an accurate pinpoint landing without help from the ground. I know that what's being looked at now for lunar landings is a pattern recognition system that'll recognize the pattern of craters automatically. But of course, we did not have that. So we had to correct the position of the landing site. I should say the position of the limb, but it turned out the quick way to do that was to correct the landing site in the other direction. So that was a software change that we made between Apollo 11 and Apollo 12 to make that possible. It amounted to a new noun, a new input noun that allowed them to shift the landing site according to a number computed on the ground from ground tracking. Next slide. And it was also the beginning of fun for me in another sense also, because I became acquainted with this, which is the LIM mission simulator at the Kennedy Space Center. Pete Conrad invited Alan Klump and I down to discuss the Pinpoint landing almost as soon as Apollo 11 had splashed down. And we got to fly this simulator for the first time. And during the coming next several years, I repeated that a number of times, sometimes flying it with one of the mission commanders, but flying it quite a bit myself. It had very good visual displays, which originated in that sort of canopy affair that's in the middle distance. Everything painted green relates to the limb. Everything painted brown relates to a command module simulator that was in the same room. You can see the control console with a few people standing around it on the left. Next slide. And Apollo 12 was successful. That's Pete Conrad standing next to the surveyor with the limb in the background, one of my favorite pictures from Apollo. Next slide. Apollo 13, next slide. Enough said. Next slide. Apollo 14, Alan Shepard there on the left, theirs was another of the fun crew training meetings. Alan Shepard, who had a reputation as a bit of an ogre in Houston, was happy as he could be now that he had a mission. Next slide. But there was a problem there too that once more involved me, and that was that a spurious signal caused by contamination was coming from the abort switch shown here to the computer, and pretty much in real time we were called on to create a workaround for that, which I was the lead person on. Essentially, since it was my software that was looking for that signal and turning the software over to the abort programs, if it saw it, it was up to me to figure out how to defeat my own code. Next slide. Oh, that's some pictures from the occasion. Upper left is a reenactment that we did for newsmen the next day. The lower right is the sort of the core group. Sam Drake, Bruce McCoy, Larry Berman, Peter Valenti, and me, with listings of some program listings in front of us, photographed in the room where we monitored missions. Next slide. That's the procedure. Obviously, I'm not going to try to go through it all now. It was not rewriting the code. It was basically using the diski to poke the code and to poke the erasable memory. We did have the ability to reach in and change any register or any bit in any register. So that's what we were doing mostly with this procedure. Next. It was also the first and maybe only time that a software guy has been written up in Rolling Stone magazine. Next. Apollo 15, next. Dave Scott's mission. The landing site was actually photographed from orbit more recently by the Lunar Reconnaissance Orbiter. That was the mission that found the Genesis rock, a bit of ancient crust going back to the origin of the solar system. Next. Apollo 16, another fun crew, John Young. Next. And another of my favorite pictures taken on Apollo 17 from a distance, I believe about 3 kilometers from the limb. And on that mission, they got as far away as, if I have it right, 7 kilometers and out of sight of the limb, which in my book is as far out on a limb as men have ever gone. Next slide. Okay, I'm just catching up here with one more angle. which is the fact that if the Mars probe led to Apollo, then Apollo led to fly-by-wire in airplanes. That's because the Apollo guidance computer was used in a fly-by-wire demonstration with an F-8 plane. The red circle shows you a disky that's mounted in the side of the airplane. Next. And now I'm going to talk just a little bit about Timeliner. I continued to work at the lab for a long time after Apollo, and we built various space shuttle simulations. I built a space station simulation and a number of other miscellaneous things. We studied the space shuttle crew interface and came up with what we call mode, spec, and DISP architecture for the crew interface. What that had to do with was that for the shuttle, it was in some particular mode, ascent, descent, et cetera, a mutually exclusive mode. Within whatever mode it was, of course, it was more divided up than that. Within that mode, there were certain things called specs, which were things that independently could happen within a given mode. And then there were displays that were simply information from the system. And those could overlay each other in almost a Windows style system in the original shuttle crew interface. Now, one of the things I developed while we were building these simulations was called Timeliner. And I'm going to have to hurry a little bit here. Well, what Timeliner is a sequencing system. It was originally built to help as sort of a paper pilot to help drive simulations. And it's built around a language that's based on temporal constructs, such as when and whenever. We realized in the early 90s that something like this was being asked for to be part of the software in the International Space Station, or Space Station Alpha, or Space Station Freedom, whichever name it had at that time. And so we proposed Timeliner for that purpose. And after a protracted period of getting NASA interested in it, it was accepted for use on the space station, where it's running right now in 3 versions. It's also running in the control center, and I understand it's being used in some form on the Dream Chaser project. The language manual, I'm giving you the NASA designation for the language manual. I don't think it's available online, but I think with that information, it could probably be obtained. Next slide. Timeliner lets you write sequencing scripts. And here's a very simple example. The unit that's installed is called a bundle. That can contain some number of sequences and subsequences. The sequences operate in logical parallel. The sequence called thermostat here, one of the things you can see there is the define capability. You see we're defining too hot as temperature greater than 80. That's proved to be a very powerful capability because it decouples the definition of a certain condition from the statements that test that condition. And you see what we're doing there is we're saying whenever too hot and the heater is on, then we turn the heater off. And we turn it off by calling a subsequence called heater off, which turns off the heater by issuing a command. Timeliner is adaptable to different hosts. And part of that adaptation is that the format of commands can be determined by the given application. And in this case, a message is also issued to the astronauts that the heater is now turned off. Next slide. And I want to say a little bit about what I think the impact of Timeliner is on software architecture, which is that if each system or subsystem can be boiled down to the control interface for it. And this, by the way, it parallels the mode spec disk thing that we worked out for shuttle, which is in use, by the way, was in use. if each system or subsystem can be boiled down to data, mutually exclusive modes, and specialists or specs that can be either on or off independently, then and those controls allow each system to do all the things it does best. If the subsystems are conceptualized that way, then something like timeliner scripts can then utilize those subsystems to accomplish some mission segment or some task. In other words, scripts that are organized by purpose, and that's analogous to the recipes you might use in a kitchen. It maps that onto the subsystems, which you could say were equivalent to the appliances in a kitchen, which are organized by discipline. So it decouples the subsystems from the sequencing and allows the subsystems to be implemented in hard code and then coordinated by relatively softer timeliner scripts that can evolve during the life of the system. I've been out of the timeliner business personally for about 20 years since I retired, 22 or 3 years, but it's still actively being worked on at the Draper Laboratory. Next slide. Well, that's the end, and there is a pyramid in the Boston Harbor that I created a few years ago. Sort of my miniature space program, a project that called for fabrication and design, had a launch that depended on astronomical factors, namely the tides, and since then has had a career moving around with wind and tides and being abused by people and birds. And thank you very much. That's the end of my presentation. Go to the next slide. That's my book. And if we have any time, which I doubt, I'd be happy to entertain questions.
Hey, Don, that was a fantastic talk. And we do have a break coming up right now, but I think we'd like to ask you a few questions if you don't mind. I actually have a comment as it relates to one of our prior keynote speakers. You may not have seen it. Steve Thibault, the chief engineer of the space exploration sector here at the Applied Physics Lab. His talk was about having to update software potentially decades after it was developed, and a statement that he made is that, you know, that the tools and technologies and the engineering practices, maybe not the engineering practice, but the tools and technologies that we use today are the archaeologies of tomorrow. And I'm wondering your perspective on kind of that maintenance effort, and, you know, as you've seen it throughout your career, and you know, what would your reaction be to having to update the software, and, you know, perhaps maybe at different points in time, and at what point you would think it just is just unfeasible?
Well, I'm not sure how to answer that. And of course, during Apollo, it was a constant evolution of the software. We weren't so much maintaining it as trying to add capability and avoid any pitfalls, which was not quite the same as maintenance. I'm sorry, I don't think I have the perspective to answer that question.
Okay. Next question from Brandon Haber. Do you have any advice for young software engineers on trying to build the best spacecraft they can?
Never overlook a clue. That was something that Alan Klump, my mentor, used to say. You know, you know, a subtle clue may be your only hint that something is badly wrong. And I can certainly name some very you know, public examples of that. The Hubble mirror. You know, there were tests that showed that the Hubble mirror wasn't quite right, but it wasn't fully analyzed and understood, and as a result, a faulty mirror was launched, and a very costly save the day effort had to be launched. And of course, the blow by of the seals in the solid rocket boosters of the shuttle that brought down Challenger was another case where things were explained away instead of being fully understood. So in big things and in small, try to never overlook a clue.
Excellent. And maybe one more question from Khalid. During your career as a flight software developer, what were the biggest changes that you observed in software design patterns or development attitudes?
Again, it's kind of a little bit too vague a question for me to quite get my, I think if I thought about it, I might have a better answer. Of course, our tools became better, you know, in the sense that we had our own computers on our desks. But I don't know that things fundamentally changed so much. You know, my experiences with building actual onboard stuff as opposed to simulations, what came at the beginning and end of my career, Apollo on one hand, and when we were adapting Timeliner to the space station on the other. And in that second case, we were building a system that had to fit into a larger system. So we were really trying to make a translation between our way of thinking and the host system in that case.
All right, great.
That answered your question, but forgive my ruminations.
All right. Do you want to take a couple more questions, or?
I'm happy to, if you have the time.
All right. We'll take one or two more, and then we'll take our break. So next question from DJ Byrne. So Don, you touched on flow down from requirements to software, and that sounds really familiar. What are the best experiences you've had getting from system engineering to software engineering to testing? And are there organizational decisions that fertilize the smooth relations?
I think there are organizational decisions that matter. But again, you know, as I observed, it was sort of a special case. I think in the 1960s, the managers realized that the only way the job was going to get done at all was if they trusted the kids like me, and basically protected us as much as possible from whatever pressure was coming down from NASA, and let us do our job by trusting us. And I think that same paradigm applies, universally if you're trying to do something difficult. Of course, flight software is still difficult, but it's now not a new field. You know, one of the things that made my time during Apollo so interesting was that it really was at that time a wide open field. There's no other way that a junior software engineer like me should have been flying simulations with Apollo mission commanders. And that could never happen now. So I don't think, or at least not within the NASA system. Maybe some of the people listening will see analogies within their own area. So it was a special case, but insofar as that sort of magic sauce that we had could translate into modern times, I think it's a good thing.
All right, great. One more question from Ron Smith. We often have to think about how software can fail, like out of bounds inputs, etc. What type of fault tolerance or recovery did your software use?
Well, one big part of that I've already talked about was the restart protection that allowed us to recover both from hardware and from software faults. Since we had a super reliable computer, we didn't so much have that to worry about if the power stayed on. Would you repeat the question?
Oh, let's see. I may have.
Okay.
Okay. So you said we often think about how software can fail, like out of bounds inputs, and what type of fault tolerance or recovery did your software use?
Yeah, well, I think explicitly about all I can cite for that is the restart protection. The one of the other virtues that we had, not that we had, but the situation made for us, was that we all knew each other and talked to each other and were in the same building and we communicated. But better communication would have changed so many of the things I've talked about. On limb one, if we had known that the arming of the engine was going to be delayed, that problem would not have bit us. If the mismatch that had been identified before flight, if the mismatch between the reference signals that could intermittently cause the flood of pulses that happened on Apollo 11, if that had been taken more seriously, if that had been communicated to the right people, and if its danger had really been understood, that would have made a difference. If there was another complete problem that I didn't talk about at all in this talk, which was that there was a problem with the time lag of the throttle of the descent engine that was caused by the fact that the published information was wrong. The engine had been improved to react faster to its throttle commands. In the thinking of the engine designers, oh, great, we've improved the engine. But the trouble was the data still had the old number in it, and we were modeling according to that number. And as a result, we nearly had an unstable descent engine throttle on Apollo 11 and Apollo 12, another case where the communication was imperfect. And back to the Apollo 11 one, I was bragging that we all talked to each other. But if George Silver, who had seen the problem with the rendezvous radar interface, had told me, if the word had gotten through to me, or if he had made a bigger stink so that we all would have known about it, then in fact there was an easy software fix for the problem on Apollo 11. So I would say the communication both is where so many of the problems lay.
All right, great. So maybe with that, we'll let you go and we'll take a break before our next presenter. I wanted to thank you very much, and also comment that I love how you're also an artist. I think there's an overlap, a really nice overlap between artistry and engineering. So thank you for sharing your insights and wisdom with the Flight Software Workshop community.
Well, I agree with you. I think my secret weapon as an artist is being an engineer, and my secret weapon as an engineer was being an artist. So
I agree wholeheartedly. And so folks, think about Don's book, Sunburst and Luminary, an Apollo memoir. All right, so thank you very much, Don, and we will take a few-minute break and resume at 2:10 with Anish and Concurrent.
Thank you. It was a pleasure.
Thanks, Don.